In this video, we will discuss calorimetry, which is a way of studying heat transfer between objects. So if we have two objects that are at different temperatures and we place them in contact with each other, the thermal energy from the hotter object will flow from the hotter object to the colder object. So heat always flows from the high temperature object to the lower temperature object. The heat flow will continue until both materials reach the same final temperature or until they are no longer in contact. The amount of heat energy lost by the hot material will equal the amount of heat energy gained by the cold material. And this is consistent with our first law of thermodynamics. Energy can't be created or destroyed. So if we lose some energy from one location, it has to go somewhere else. So the energy that is lost from the hot material goes into the cold material. What this can do for us is it enables us to monitor the change in temperature of one object and infer the amount of heat that was gained or lost by a different one. So let's say we have a block of metal at 55 degrees Celsius and we add it to water that's at 25 degrees Celsius. Well, the hotter object is the metal, and so it will transfer thermal energy into the water. The thermal energy transfers from the metal to the water, and the exact temperature change depends on the following: the mass of the metal, the mass of the water, and the specific heat capacities of the metal and the water. Now, we previously said that via the first law of thermodynamics, energy can't be created or destroyed. So the energy that comes out of the metal goes in to the water. So the hot object, the metal, loses some thermal energy. The water picks it up. Now you'll notice that there's a difference in sign. And again, remembering that Q is the variable that we use to represent heat. There's a difference in sign. And in a previous video, we talked about how the sign indicates the directionality of energy flow. A plus means energy is flowing into the system, and a minus means that it is flowing out. So in this case, the metal energy is flowing out, the water energy is flowing in. So because they are opposite in direction, there needs to be a negative in front of one or the other of them so that they will be the same sign, right? So the Q for the metal would be a negative number, and the Q for the water would be a positive number. So to make them have the same sign, we put a negative in front of the Q water, and then they are both negative. We could also put a negative in front of the metal, and then they would be both positive. The key part here is that they are the same. So you either put a negative in front of the water or the metal. It doesn't really matter because of the directionality of the energy flow. Now we can replace our Q value with our expression for our specific heat capacity, which is the mass of your object times the heat capacity of your object times the change in temperature is equal to the amount of heat that flowed in or out of your system. We have the same thing for water. For these, you will find it useful to subscript your variables. And the reason for that is we have two different masses. One is the mass of water, one is the mass of the metal. Similarly, your specific heat capacities are different. The specific heat capacity for the metal is a different value from water. Water tends to be more than most metals, and so you need to label it so you're clear on which one you are talking about. Now, the process of calorimetry often gets done in what are called calorimeters. These are laboratory equipment which are intended to closely monitor the flow of heat from one location to another. In a lot of laboratory experiments in school, a common method for looking at calorimetry is to use what is called a coffee cup calorimeter. The reason it's called a coffee cup calorimeter is you take two styrofoam cups, similar to what you would buy coffee in, and you perform your reaction in that solution. you have a thermometer and then something to ensure that the solution is homogeneously mixed, so some sort of a stirring rod. Typically in educational settings, it's an aqueous solution reaction. So you perform your aqueous solution reaction in your coffee cup calorimeter, monitor the change in temperature of the water or the solution, and from that infer the change in heat or the change in enthalpy, the amount of thermal energy of the particular reaction that was going on. So in this particular setup, the reaction is done in an aqueous solution and at constant pressure. The reason we know it's at constant pressure is the styrofoam is not too stable, and so if it was done under higher pressure, the styrofoam would break apart. Plus, you're only putting a cork lid on top. It is loose fitting, and so if the reaction produced gas, the gas would escape. So the pressure is constant, it is open to the atmosphere. So whatever pressure the environment around the coffee cup calorimeter is, that's the pressure that's being exerted on the top of the surface. The calorimeter is often, in this case, a nested set of foam cups containing the solution. So the way that we do this process is we do our chemical reaction. The heat that's coming off of the reaction is equal to the amount of energy that's being absorbed by the solution. Typically, the solution is treated as being water because most of the time the reactions are done under dilute solution conditions. So the energy is flowing out of the reaction, flowing in to the solution, although they are sort of intermixed, and so the boundaries are not quite as clear. We can replace our Q solution with our specific heat capacity equation. So we have Q reaction is equal to the negative of the mass of the solution times the heat capacity for the solution times our change in temperature. Now, because this is being done under constant pressure conditions, the Q reaction is equal to the delta H reaction. Although a lot of times the delta H reaction gets divided by the number of moles because enthalpy of reaction is typically written in joules per mole, whereas the Q value is often written in terms of the total amount of energy that was released as opposed to the energy per mole. So let's take a look at one type problem that is just what we had previously described, right? So we have two solutions initially at a particular temperature, 24.6 degrees Celsius, that are mixed in a coffee cup calorimeter. When a 100.0 milliliter volume of a 0.100 molar silver nitrate solution is mixed with a 100.0 milliliter sample of 0.2 molar sodium chloride solution, the temperature in the calorimeter rises to 25.30 degrees Celsius. We are tasked with determining the change in enthalpy, delta H reaction, for the reaction as it is written below, right here. Assume the density and heat capacity of the solutions is the same as that of water. So we're going to use the density for water. The density for water is 1.000 grams per milliliter at about 25 degrees Celsius, which is what we're dealing with here. The heat capacity, C sub S for water, is 4.184 joules per gram degree Celsius. That is something that would either be provided, well, on an exam, it would be provided. In a homework question, you might have to look it up. Okay, so we have our reaction here. You'll notice that we have the same volume but different concentrations, and so we're going to have a limiting reagent situation. So we got a couple different things going on. In terms of what's actually happening is we have our coffee cup calorimeter, and we have two containers. Everything is at the same temperature. One container is silver nitrate. It has 100.0 milliliters, 100.0, and this is 100.0 milliliters of sodium chloride. Okay, so we are mixing both of them together. What this tells us is that the resulting solution would have a volume that's equal to the sum of the two. So after we mix them, the total volume is going to be equal to 100 plus 100, which is 200.0 milliliters. Okay, so we're talking about energy transfer, and so we're going to use the Q is equal to mc sub s delta T. We're talking about calorimetry. This is our general equation relating heat to our heat capacity. Now, we have the reaction of the silver nitrate and the sodium chloride occurring in the water. So, our Q, the change in heat, or the heat released by the reaction, is equal to the negative of what we measure for the solution. You can think of the reaction as occurring here. The heat is coming off and going into the solution. So the energy is released from the reaction, goes into the solution, and so they are opposite in direction but equal in magnitude. We can then replace our Q with our heat capacity equation, which would be minus M, and this is solution times the heat capacity of the solution times our change in temperature, which is T final minus T initial. Right, so we have our final temperature, 25.30, our initial temperature, 24.60, and so that will give us our change in temperature. Okay, so our Q for our reaction is equal to the negative of, we can now plug our numbers in, the mass here of our solution is the volume total times the density. So this would be 200.0 milliliters times 1.000 grams per 1 milliliter. Our milliliters cancel out. We'd be left with grams of solution. Multiply this by the heat capacity, which is 4.184 joules per gram degrees Celsius. Our grams cancel out. And then if we multiply this by our change in temperature, which would be 25.30 minus 24.60. Now, a word of sort of caution, but clarification. Because we're talking about a change in temperature here, you can use Celsius or Kelvin. So depending on where you're looking online, you'll see some examples of them using Celsius, some where they're using Kelvin. The key part to doing that is to make sure that they are both, the two temperatures that you're working with are both either Kelvin or Celsius. Because we're looking at the change in temperature, it doesn't matter which one you're using. The gradation, or the difference between two values, for Celsius is the same as the corresponding difference between the two values for Kelvin. Right, so 1 Celsius is equal, 1 change in Celsius is equal to 1 change in Kelvin. Okay, so this comes out to be, our Q reaction is negative 585.76 joules. Now, our Q, right, has units of joules. Our H has units of joules per mole. So our delta H reaction is essentially our Q for our reaction divided by the number of moles of reaction that occur. So because we have two different because we have the same volume and two different concentrations, one of our components is going to run out first. If you look, the one that will run out first is the silver nitrate, right? And that's because it's 100 mils with a concentration of 0.1 molar, whereas the sodium chloride is 100 mils of 0.2. So there's twice as much sodium chloride as there is silver nitrate, and by our balanced chemical equation, it's a 1-to-1 ratio. So this tells us that the silver is going to run out first. The number of moles for the reaction then is equal to the number of moles of silver nitrate that we have, which would be equal to 0.1000 liters times 0.0100 moles per liter. And this works out to be, let me make a little bit of room. This works out to be 0.01000 moles. Okay, so we can take our value for our Q. Our Q in this case is equal to our delta H if we divide the Q by N, because we're working under constant pressure conditions, right? In a coffee cup calorimeter, we're working at constant pressure. So our delta H reaction will be equal to negative 585.76 joules times 1 over, this is the same as dividing, by 0.0100 moles of reaction. This will give us negative 58576 joules per mole. Make a little bit of room. This then comes out to be, we can convert it to kilojoules and do our significant figures. The value on the bottom, our moles, has 3 significant figures. Our temperature and our heat is going to end up having 3 significant figures because our subtraction here, this value is going to end up having 3 significant figures. So our end value would be negative 58.5 kilojoules per mole. Okay, we could keep it in joules and have 58,500, but a lot of times if it's greater than 1,000, you end up converting it into kilojoules. Another problem, which is about as complicated as we can get for these heat capacity problems, is let's say that we're trying to figure out what is the final temperature if 125 grams of copper pellets at 100 degrees Celsius are dropped into 25.0 milliliters of water at 20 degrees Celsius. Okay, we have our heat capacities and we have our density for the water that we're going to be working with. So we are essentially looking at, we have a container, has some water in it, and we have a big bunch of copper that's at 100 degrees Celsius. We're dropping it in, and this is 25.0 milliliters, and it's at 20 degrees Celsius. Okay, so the warmer or the hotter of the two objects is the copper, so energy will be coming out of the copper going into the water. So we can start with an expression for how the heat is flowing. The heat of the copper is equal to the negative of the heat for the water. Right? If energy is flowing out of the copper, it's going into the water, and so they're going to be opposite in sign. We can replace our Q values with the heat capacity equation, the specific heat capacity equation, giving us mCu, the mass of copper, times the specific heat capacity of copper times the change in temperature for copper is equal to the negative of the mass of our water times the specific heat capacity of water times our change in temperature for the water. For this particular problem, it's going to be very helpful to sub-label everything so that we can keep track of all our units. We're going to approach this algebraically, solve everything algebraically, and then plug in the numbers at the end. Okay, so we're interested in the final temperature. Because these two things are coming into contact, our temperature final is going to be the same for each, right? The copper will continue to give up thermal energy to the water until they reach a thermal equilibrium where both are at the same temperature. So the final temperature for both is the same. Because we're trying to find our final temperature, we need to break our change in temperature here up. Now previously we had said that as long as you're working with change of temperature, Celsius or Kelvin will work perfectly fine. But because here we're not looking for the change, ultimately we're trying to find the actual value. Because we're trying to find the actual value here, we absolutely need to be working in Kelvin. So we need to break up our change in temperatures into their temperature initial and temperature final so that we can get at our final temperature. So this would be MCU times C sub S for copper times temperature final minus temperature initial for copper. This is equal to minus M, the mass of water, times the heat capacity of water, times temperature final minus temperature initial. Okay, we're going to distribute in our values here and here to help us get rid of the parenthesis. So this gives us mass of copper times the heat capacity of copper times temperature final minus the mass of copper times the heat capacity of copper times our temperature initial of copper is equal to the negative of the mass of water times the specific heat capacity of water times our temperature final minus the negative of the mass of our water times the specific heat capacity of water times our initial temperature of water. Here we have subtracting a negative, which in essence is the same thing as adding. So we can combine our two negatives here into just a plus. So plus. Now, what we're trying to do is get temperature final as our answer. So we need to isolate it. So we're going to move everything with temperature final to one side. So we got temperature final in here, temperature final there. So I'm going to take my value here, and I'm going to move this to the other side. So I will add that value onto both sides. I also want to get everything that doesn't have my final temperature to the other side. So I'll take all of this and move that to the other side. So that would give us mass of copper times the specific heat capacity of copper times the final temperature plus the mass of water times the specific heat capacity of water times the final temperature. That will be equal to the mass of water times the specific heat capacity of water times the initial temperature of water plus what we had over here, which is the mass of copper times the specific heat capacity of copper times our initial temperature of copper. Now we're going to get our temperature final all by itself, right? So we can combine our terms here, these, put them in a set of parentheses with temperature final outside. So temperature final times mass of copper times the heat capacity, the specific heat capacity of copper, plus the mass of water times the specific heat capacity of water is equal to what we had before, which is the mass of water times the specific heat capacity of water times our temperature initial of water plus the mass of copper times the specific heat capacity of copper times the initial temperature of copper. Okay, so we can actually divide both sides by what's in the set of parentheses. All right, so this would be mass of copper times the heat capacity, specific heat capacity of copper, plus the mass, this is H2O, mass of water times the specific heat capacity of water. Okay, divide that by mass of copper, specific heat capacity of copper, plus the mass of water times the specific heat capacity of water. On the left-hand side, everything in the parenthesis on top is canceled out by the stuff on the bottom. So we're left with what we want, which is an equation for our final temperature in terms of values that we have. It's a lot of numbers, but we have all of them. We have our mass of our copper. We have the volume of water and the density, which means we can get the mass of the water. We have our initial temperature here. We have our initial temperature of water. And we have our two heat capacities. So we have all the numbers. I'm going to erase some stuff to create some room, and then we're going to plug in our values. So we can put in our values for our equation that we worked out. Our temperature final is equal mass of water, which is 25 milliliters times 1 gram per mil, which would be 25 grams. So 25.0 grams times the heat capacity of water, 4.184 joules per gram Kelvin, times our initial temperature. Now for our initial temperature, we do need to work in Kelvin. We are not talking about changes in temperature. We're talking about the actual starting temperature. So it needs to be in Kelvin. So 20 degrees Celsius plus 273.15 is 293.15 Kelvin, plus mass of copper, 125.0 grams, times the heat capacity, 0.385 joules per gram Kelvin, times our initial temperature for copper, which is 100 degrees Celsius plus 273.15, so that would be 373.15 Kelvin, and that was from our original drawing. Okay, we're going to divide all of this by the mass of copper, 125.0 grams, times the heat capacity, 0.385 joules per gram Kelvin, plus the mass of water, 25.0 grams, times the specific heat of, or the specific heat capacity of water, which is 4.184 joules gram Kelvin. Okay, before we come up with a number, let's take a look at our units. Our grams here, cancel all those grams, these grams, cancel all those grams. Gram cancels out gram, Kelvin cancels out Kelvin, gram cancels out gram, Kelvin cancels out Kelvin. Then we are left with joules on top. So the joules on top will cancel out the joules on bottom. So our unit, we're left with 1 over Kelvin when we add everything together. And 1 over Kelvin is the same as Kelvin. So we're left with our final temperature in Kelvin. Plugging all that in to get our final temperature, our T final, is equal, everything on the top comes out to be 48,621.33 joules divided by 152.725 joules per Kelvin, right? And so our joules end up canceling each other out, giving us Kelvin. Plug this all in, and you get 318 0.3587 Kelvin. In terms of significant figures, our top value is going to have 3 sig figs. Our bottom unit will also have 3 significant figures. Yeah. And so this will work out to have 3 significant figures. So, converting this into Celsius, we will get 45.2087 with our sig fig there. So that works out to be 45 degrees Celsius would be our end temperature. Right? So you can see that although the copper weighed a lot more than the water, right? We had about 5 times the mass of copper, and the temperature was very high, it was 100 degrees Celsius. The end temperature for both of them together is actually closer to the water than it was to the starting point of the copper, and that's because the heat capacity for water is so high.